Hello everyone, Greg Risterman here from Olympus. I'd like to welcome everyone today to this webinar titled The PipeWizard, Zone Discrimination Theory and Technology for Pipeline Inspections. This webinar includes an introduction to phased array zonal inspection theory and technology based around the PipeWizard automated pipeline inspection system. Our presenter today is Nicholas Bublitz. Nick is a global product support specialist for Olympus and has been involved in technical support management, and global technical support focusing on phased array, TOFT, and automated system technology. This informational webinar will last approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of the screen during the presentation. The chat panel is not used for Q&A. If we are not able to get to your question during the live event, they will be addressed personally, either by email or by phone after the event. Now, without further ado, I'd like to turn the presentation over to Nick Bublitz. Nick, take it away.
Thanks, Greg. I just want to echo Greg's sentiment about welcoming everybody and thanking everybody for joining us this morning. I know everybody can be quite busy, and it looks like we got people from all over the world, so it's a great event today. Like Greg said, we're going to go over the PipeWizard and zone discrimination theory and technology a little bit. The goal will be to kind of demystify the zone discrimination technique, look at the equipment and process requirements, kind of what goes through typical zone discrimination inspection, and just go from there. Hopefully at the end we'll have a little time for questions, look at a little bit of data to kind of highlight some points, and also the setup. So without further ado, we'll go ahead and get started. So here what we're talking about today is basically girth weld inspections. So we're talking about either onshore or offshore inspections. These typically have some unique requirements that we'll look at that often lead to using a specialized technique with a system that we call the PipeWizard. So we'll look at that in detail, but these are some of the conditions that we would typically use this system anywhere a pipeline is being built, either onshore or across country. Sometimes in fabrication shops, the system can be used, and also in offshore. So obviously, these type of conditions obviously require specialized equipment, both for conditions as well as the technique. So when we talk about the codes that typically govern this inspection, just to get started, we're typically talking about two different main bodies of code, which is API 1104, which typically dictates the onshore requirements. And for the offshore requirements, the typical inspection code is DNV OS F101. Now, these codes by themselves are not really subject to 100% zonal technique. It's really a tie-in to a document called ASTM E1961 that requires a zonal discrimination technique. So these are just a few documents that if you may have them or you may want to look into it further, these are typically the codes we use. So a lot of us in the last couple of years have become really familiar with phased array inspections. We're looking just at mainly weld inspection here. But typically when we use a portable OmniScan type unit or even industrial type unit, typically we're using two types of inspection, usually a sectorial multi-angle scan or a linear or electronic scan where we use a fixed angle, number of elements, and fire to get that angle. And typically we use either a semi-automated scanner, like here on the bottom left, or a fully automated scanner. And this is typically okay because the typical bevels we see in construction welds and other types of welds are typically fairly prone to being covered with this type of inspection. When we look at some of the pipeline requirements, so here we're looking at a typical weld that we're used to with a bevel of 30, 33 degrees, something like that. Typically for the general weld inspections that we probably are more familiar with using sectorial linear scans, we choose a number of elements and we can fire a sector scan, focus on the weld, no problem getting the proper incidence angle here. And we can electronically change that and get a full volumetric coverage and good detection of our defects. When we look at typical pipeline joints, often they're engineered with very narrow bevels, so 5, 10 degrees. Even though phased array, sectorial scans, and linear scans are great, they can provide a lot of coverage and detection capability, there's still pulse echo ultrasonics. So when we have an incident angle that is so narrow, it can be very difficult to get the sound back to the probe, especially for the fusion line. So this is where we usually, from a technique perspective, might want to look at a zonal technique or a pitch catch technique. So if we had normal pulse echo, this might never come back to the probe just because of the narrow incident angle. So automatic welding, a lot of times we have a very narrow bevel when we make pipeline joints. So in order to make sure that we can detect especially lack of fusion and hit that bevel angle at the proper incident angle for detection and sizing, what we normally do in a zone discrimination technique is look at the joint design and then split the weld into various zones. So you can see here, depending on the weld geometry, its thickness, etc., we're able to designate zones between 1 and 3 millimeters typically. And we have things like the different fill zones in the weld here. We have a cap channel, hot pass, the root, etc. Depending on the configuration, we'll split that up into zones. And then what we can do is basically, instead of using a group of elements and doing a pulse echo technique where the sound comes back to the same group of elements like we would with an omniscan or a sectorial scan, we can actually use a pitch catch technique. So this is a very similar probe. In this case, we often use a 60-element probe. But instead of doing the pitch catch from the same number of elements, what we've done is for each zone that we've highlighted is select a number of elements to emit the sound and a separate number of elements to receive the sound. What this allows us to do is pitch the sound in to the different zones and then be able to receive it back at the receiver. So where pulse echo might be reflected off in an area where the probe might never see it, this pitch catch technique allows us to inspect very narrow bevels. So in this case, we'll have a beam per zone, and each separate grouping of elements will only be firing a single ultrasonic beam. So what we're really doing is just varying the use of phased array to fit our application. So here in the case, we have 5, 6 zones, and then we make sure those overlap so that we get more than 100% coverage. So we look at the inspection layout like this, and then we use a strip chart recorder to do very fast analysis, know where the defect length, amplitude, etc. is. And we'll look at that in more detail as we go through. So in this case, we have 3 millimeter zones. Again, depending on the configuration of the joint, those can vary between usually about 1 to 3 millimeter. So when we form zones, we basically look at the joint configuration, and every joint pipe thickness might have different zones affiliated with it. So this is just one example where we split the zones based on the welding, and then we would designate different target areas in order to do the inspection. That is translated to basically a strip chart recording. The thing with pipeline, either onshore or offshore, is typically want to do the manufacturing of the pipe as well as the inspection very quickly. So we typically, a lot of times, will follow right behind the welding process, and the system is very fast. It doesn't really do any good unless the analysis and reporting can be fast as well. So the entire system is really designed around speed and ease of analysis. So if we looked at the technique a little bit and how the probe would be working and breaking the weld into zones, this is what the analysis typically would look like. So we have both sides of the weld, an upstream and a downstream. We'd have a probe on each side of the weld. And then just like we saw the weld broken into zones, we have each zone here from each side of the weld, a few volumetric channels. Typically these zones are focusing mainly on the bevels for lack of fusion. We want to make sure we don't miss any internal defects as well. And then we also have coupling channels. We want to make sure that the probes are adequately coupled all the way through the scan. There's no coupling problems affecting transmission of sound and therefore detection of defects. So we'll look at this a little bit bigger, but just kind of trying to lay out the general process at this point. So this might be what typical output would look like if we had a scan with no welds. Typically we use color coding and some other tricks so that we can look at a full volumetric scan 360 degrees around the weld and immediately key in on areas that might need investigation or sizing. We'll look at those color codes so they make a little more sense, But here you can see this one. We got some reds and yellows, some other things that are going to bring our attention to those defects to do further analysis. So the typical inspections that we do with this type of system, the main system is just usually used for circumventional welds. There could be adaptation to long seams, but that would have to take an investigation. The general system off the shelf is really designed only for circumventional welds. Really any type of weld profile can be done. CRC Evans, J bevel, V, double V, X. It's just going to alter the inspection technique, how we break it up, and how we apply the ultrasound. The typical range for the standard PipeWizard system is about 6 millimeters to 35 millimeters. And it doesn't mean that things can't be done for thinner and thicker. We just have to adapt a little bit in order to apply the same technique to thicker or thinner pipes. Typical diameters are 6 inches to 56-inch outside diameter. Again, we do have specialized the cases in the past where if we need to go lower or higher, it's just a variation of mechanics and the technique a little bit. Pipe materials, carbon steel by far is the largest standard, but it can be adapted to Inconel, cladded pipe, seamless pipe, pipes with wall thickness, which we'll look at a little bit later. We just have to maybe alter the technique again. Some of these austenitic type materials or ones with cladding often don't propagate well with shear waves or don't get reflections back. So we can do some special things there. We just have to look at each case individually. So look a little bit at the instrumentation. This is actually what we call our PipeWizard V4 or version 4. It's been recently changed. Before this unit, there was a version called the V2, which was kind of widely used for a number of years. So we've done an update of our electronics system in general in the last couple of years. We use a standard Focus LT 64128. So if you know with our product line, the hardware architecture of this is very similar to a product we sell for a lot of times just for general weld inspections or industrial applications. The main difference is this obviously needs to be ruggedized. It needs to operate in very harsh environments. So the next couple of slides we'll look in more detail about some of the casing and some of the protection put on the unit. This unit runs basically on a band, a CRC type band. It's kind of hard to see in the picture here. We'll see if we'll have it a little bit later. This is the same type of band that an orbital automatic welding system would run on. And the reason for this is when we looked at the pitch catch technique, it's very important that the mechanics of the system can hold the probe to a very tight position. If we're only using one beam to fit in on a very focused zone, we need to ensure that probe doesn't have a lot of movement. When we do general phased array, using sector scans and linear scans, we often use less ruggedized scanners or ones without less positioning because we have overlap. But in this case, when we have individualized zones, it's very important that probe doesn't move or the received sound might not come back to the correct grouping of elements. So the PipeWizard itself, V2, V4, has a very strong field experience. There's hundreds of units in the field, millions of welds have been inspected, and there's hundreds of operators out there trained on the PipeWizard system. If we look at a little bit of what's happened, this is actually the old version of the PipeWizard called V2. So housed inside of the plastic housing, we basically have a motor controller, the acquisition unit, some other controls. What we've done in the last number of years is really reduce the size of that unit. Also add some extra protection as far as IP64, reduce the weight. So this lower unit is about half the size, half the weight, and we still have the motor controller, all the electronics inside of a sealed case so that we can operate in those harsh environments. This is a little bit closer look. So here, if we look at the front casing, we have the ability to insert 2 phased array probes. We have motor controller connectors, power, connection to the computer, etc. So it's really just a phased array unit that's been ruggedized for field use. Backside, a fan so that we can operate in a sealed environment and keep the unit cool. And so if we need to transport it, modern electronics have really made this much easier. A much smaller unit we can throw in the back of a pickup or easily transport from place to place. If we look at the PipeWizard scanner a little bit, we talked about that in order to be accurate and use the zone technique, we need to be very rigid in our mechanics. Here we see the clamps that clamp onto the CRC type welding band. And this ensures a very tight positioning of the whole scanner. On the left, we're looking at the underside of the scanner. We can see how small the carriage is when we only use 2 phased array probes to be able to get full coverage of the weld. Often we'll use a larger carriage and we can add time of flight diffraction. And other slides will also show some other adaptation for other ultrasonic needs. So here we look at a transverse module. So if I go back just one slide, here is a connection. We'll be able to connect another module onto the unit, expanding the footprint of it. And now if we need to shoot across the weld, we often use just conventional ultrasonic transducers to look for things like transverse cracking or transverse defects if there's a requirement for that. So it is adaptable to different ultrasonic techniques. So this is the new main phased array electronic that we would use today. In this case, it has phased array and time of flight diffraction on it. And really what this has replaced in the last years is an old multi-probe system. Before phased array was widely available, we used to use old multi-probe scanners. So these would have 20, 30 some transducers that we would try to position very, very accurately in order to have one single conventional beam hitting our required zones. We can imagine the trouble with this, very precise. We have many, many different parts that can move. If one transducer becomes misaligned or if the scanner's dropped, we're basically not getting the full coverage of it. So now with phased array, we're able to replicate all those beams, actually get even more coverage than we could from 30 UT probes, and the mechanic is highly reduced. So holding the position of 2 phased array probes is much more reliable than the systems that we used to use using multi-probes. One other thing we've done, improving these type of inspections with improved technology, is just like our COBRA system and some of our manual applications, we started to improve the probe technology. So these are called CCEV, which basically means concave curvature and the elevation or width axis of the probe. So here we can see a normal linear array would have a flat width to it. We just take elements, we dice them, and there's no curvature in the passive axis. Well, we often draw ultrasound as a straight line, but we know that we have beam spread basically in both axes, both in the forward direction we're shooting as well as side to side in the lateral direction. So by mechanically putting a curvature on the elements inside the case, what we do is we reduce the beam spread in the side to side or lateral dimension. And what that really does from an ultrasonic perspective is it gives us better length sizing. If we have a less smaller beam and the passive axis, we're able to do length sizing the direction the probe is moving at a much better rate. So here we look at display of both a non-focused old type of probe as well as a focused new probe. You can see just even on the strip chart how much tighter and concise each indication is. This is basically because as we pass over the notch, the defect or the flat bottom hole, we have a smaller beam spot size, and it's able to give us a better resolution. So in this case, we have a 3mm refractor in a calibration block. If we were to do a 6 dB type sizing technique using a non-focused probe, in this case we get a 6mm measurement. So that's because the beam width, using the focus probe, using the same sizing technique, you can see we can precisely size in the length axis due to the smaller beam spot size. So it's just one improvement on the probe technology, and we can apply this to all kinds of phased array. So look at high accuracy. Basically, one of the benefits of using ultrasound is that we can very accurately size the defects. So these are some etchings, some micrographs of different defects. After qualification, we often cut them apart, measure the defects directly. So here we get very good sizing, especially in the height axis, that we don't get usually with radiographic techniques where we can only determine the length. So in most phased array PipeWizard projects, we usually can demonstrate an accuracy between 0.5 millimeter and 1 millimeter when we're sizing the defects, which is very important when we start to look at critical assessment, reject rates, et cetera, as we'll see in the next coming slides. Just take a little look. Often these pipelines are radiographs, so we look at phased array ultrasound as an alternative. Often there's several advantages. From high probability of detection. For one, ultrasound has a better probability of detection in general for lack of fusion, as well as crack or other type of linear defects than radiography does as a method. We get very accurate sizing of defect height, which we typically don't get in radiography. And that really causes less repair using what we call ECA, or engineering critical assessment. When a pipeline or anything is designed, often there's an engineer that knows what size defect will allow that pipe to continue operation. In order to apply this type of criteria, they have to know both the length and the height. They have to have a volumetric measurement. So if we only apply radiography, typically we only have the length. We can't go back to this criteria and allow longer defects with small height that we could. And we'll look at this in a few slides to give a few examples. Of course, with ultrasound, there's no radiation, no hazard, no licensing. There's no screened off work areas. So, typically when we do these pipeline inspections, we're either offshore on a boat that is crowded with other people working, doing other tasks, or in a pipeline where the welder operation is very close. Maybe we're a weld or two behind. So having radiation areas where we need to screen off or we can't work can be very cumbersome. So obviously ultrasound is a safe alternative, and it's really good for other processes to go on at the same time. Typically no chemical, no waste material. Our coupling is just water, or if it's a very cold condition, we might use a methanol mix, but that can usually be captured. We don't really have any waste material from producing film, this kind of thing. And one of the huge benefits is real-time analysis. We saw the strip chart recording. We'll see that a little further in the slides and maybe actually in the program itself. Based on the strip chart recording, we're able to quickly see if the weld is good. This is really critical for especially offshore, because often as soon as the pipe is inspected, they want to be able to take the pipe and install it underwater. And even onshore, we want to keep up with the welding process. We don't want to be too many welds behind. So the strip chart type recording really allows real analysis. We use some colors, some other things. We can quickly tell, yes, the weld is okay. And also if there's a trend in the defects, we don't have to wait for film to be processed and then try to link them together to see if there's a trend, especially with the automatic welder. Something can go wrong. If we're getting the same type of defect that's happening in the weld, with this type of ultrasonic technique, we're able to instantly tell a problem in the automatic welding process and give that feedback to the welder to correct it as soon as possible. And then, of course, set up an inspection reports in electronic format. We're able to digitize everything, save onto hard drives, be able to recall that data, and reevaluate it, reprocess it in a myriad of ways indefinitely. So just look at some of the data results comparison. So here again is the cutout etchings, what it might look like in the strip chart. We'll probably have some better looks at this later, but we can see in the volumetric channel as well as the individual zones. So here we have a defect. You can tell very quickly that it covers 2 of our zones that we set up in this example. This one again, 2 main zones and going into a 3rd, just possibly. If we're looking at a radiograph, typically this would all we would have, just a length measurement and be able to measure the length but not in the position, but not necessarily the height. If we look at a little bit more, we talked about ECA, or defect allowance comparison. This is out of API 1104, the CTOD, or crack tip open displacement, Appendix A for your reference there. It's pretty old when I put this into a presentation, but it might be a revision to it, but it's really just used as an example. So this is based on a 42-inch pipe, 1/2-inch thickness. On the left here, I know it can be hard to see in the red. I'm going to highlight one specifically in a minute. We have different imperfections from inadequate penetration, incomplete fusion, whether they're connected to a surface or they're buried. And then basically we have two things in the middle. One is called standard clause. The standard clause in this case relates to radiography. If we were to use radiography as a technique, having the limit of only knowing the length, these would be the lengths of these different types of defect that we could allow without rejecting it. Over here we have a fracture mechanics column to Appendix A, and this basically is split between two columns. So when we say fracture mechanics, we can apply this when we are able to measure the length and the height. And you see there's two columns. So if the flaw is between 0 and 0.075 or about 2 millimeters high, we can allow one length of defect. And if it gets larger than that, from 0.075 to 0.150 inch, we can allow a different length because it's become more critical because of its height. So in this case, we'll just highlight one so it's a little more visible. In this case, we look at an incomplete fusion that's buried. So it's not connected to the surface. It's completely contained within the weld material. If we use radiography and we detect one of these that has 2 inches of length, it must be rejected because we're not able to measure the length. It's the same case if we're able to use ultrasonics and measure the height between about 2 millimeter and 4 millimeter. We get the same rejection criteria. But if we measure that defect and it's less than 0.75 or 0.075, a little bit of a typo there, or about 2 millimeters high, then we're able to accept a very long run of it, about 16.8 inches. So you can see, if we're able to measure those lengths, we might have many, many indications that are very short in height and do a bunch of rejects with radiography, where ultrasound would be able to accept very long runs of them as long as they are below a certain height. So typically when we go out and do a PipeWizard inspection, this is just kind of an example of the timing and the process that we would normally go through. And it's going to design a little bit depending on the condition of the pipe, type of weld, the environment you're doing the inspection in, but it's just a general walkthrough. So if we're following closely behind the welding process, we might have to quench the pipe to cool it down a little bit. Often this is necessary offshore because usually they'll have a manufacturing station set up right next to the inspection process. So as soon as it comes out of being welded, it'll immediately move down the line and be inspected. So it might still be a little warm. We'll just quench it, about 20 seconds to 60 seconds to do that. Then we'll position the inspection band on the pipe. A series of tools in the PipeWizard kit to do this so that the pipe is square and centered. Position the scanner on the band. There's basically a few clamps on the top, so we lift the scanner up, clamp it onto the band. We then move it to our inspection start position. We want to know where that position is. We have usually a typical stamped or marked 0 point because we're going to have digital data when we're done, and we want to be able to go back to a location and do a repair. Scanning the weld, the system can operate at up to 100 millimeters per second typically. This is going to vary by how many beams we have, how thick it is, all the variables. So it's really going to depend on the pipe diameter, the thickness, how many beams we're using based on the joint geometry. So this can be about 20 seconds to 120 seconds. Then we're going to do the analysis and defect marking. Typically this is done somewhat during the scanning, about 30 seconds after if there's no defects. Typically they run in tandem teams. People are out operating the scanner, and there's somebody back looking at the data as it goes through both the acquisition and after analysis. Then we need to remove the scanner, place it on a calibration block, recheck the setup, and then we remove the inspection band. So we'll talk about calibration in the next few slides. There's typically a requirement to make sure that the system is being accurate. That's more stringent offshore than it is onshore. So typically onshore, the typical inspection process is to inspect 10 welds and then record a calibration file. Now if that calibration file checks out okay, you can proceed to the next 10 welds. If not, you might have to go back and redo some inspection. Offshore, we do that every weld because after it runs through manufacturing, then inspection, it often goes directly to be placed underwater. So obviously, it's much harder to retrieve or fix. So we usually do one weld, one calibration block, one weld, one calibration block, and record every one of the calibrations to show that our inspection process was good. So here's a typical calibration block shown here for onshore mainly. We use what we call a Z block. So to reduce the weight of it, we basically have a Z-shaped. One side is basically upstream, downstream. And we'll place this kind of in a dummy pipe often to reduce the weight because depending on the thickness, the block could be very heavy. And if we have to go to remote areas, we want it to be easily transportable. So here you get a better shot at the Evans band type that we'll connect the scanner to. Inside of here, it's very thin material just for the scanner to run on. And then the actual calibration targets and where the probes are going to be physically making contact are actually on the Z block type design. So depending on the joint design, there'll be a kind of a weld center, and then we'll have different targets and zones that need to be built into a calibration block to ensure the positioning and amplitude sensitivity of the entire inspection. Here's just a bigger look. So if we have a typical pipeline job, it might look something like this. It's typically a series of notches as well as flat bottom holes for each zone, volumetric reflectors, as well as fusion type reflectors and ID and OD. And then each one of those reflectors will be designed with the zone in consideration. So here we see a bevel type flat bottom hole. And very accurately, these are placed at the proper angle to replicate a defect that might happen on that fusion line. Excuse me. So setup creation. We'll look at this towards the end. We'll actually pull up it, get a little bit bigger view. But basically what we're going to do is define which probes and wedges we're using, phased array as well as time of flight diffraction. Based on the drawing of the pipeline, we actually design the bevel in. And then in order to be quick, we not only need inspection and analysis to be quick, we need setup to be relatively quick because it obviously can be very cumbersome to program individual beams very accurately. So built into the software, once we put in the joint designation, we can basically have the software generate all the beams for us, theoretically. And then typically for the first job, the first inspection, we would typically go over the cal block and maybe make some micro adjustments while being somewhat static over the reflectors and then running over it dynamically. And there's a lot of tools built in to make this very quick. So once we get in, we're able to see that the software automatically generates for us the proper beams, both on emission and where they're going to be received and the grouping of elements that are going to do so. There's a few more illustrations. So here we'll be able to very precisely put in finite measurements for all of the joints, design and geometry. And from there, things like velocity, thicknesses, all the part geometry, and also gate settings. So you'll see in the slides coming up how important the gates are. The gates basically define our zones, and we're able to define those very well and help them to help us position flaws very accurately. Finding the probes. And again, we'll look at this a little bit. Once we have all the basic setup in, we can just say generate, and the system will actually generate all the ultrasonic beams necessary theoretically. And again, we might micro adjust those on the cal block itself. So after we hit generate, it's kind of what it might look like. We have defined zones. So these purple lines are gate positions. We define how long they should be in order to capture the fusion line as well as a small area before and after. There'll also be some volumetric channels illustrated. And then we have each beam. So this looks kind of busy because we're looking at all of the beams all at once. Just like in the last slide, we're able to say, look at individual beams and highlight them as they did here, and we'll get a better view of each individual beam. So in this example, this is a very narrow bevel, maybe 5 degrees on a 20 millimeter weld. So look at the use of sectorial and linear scans. So we mentioned earlier for the fusion line, And the main technique, sectorial linear scans might not be ideal, and that's why we use the pitch-catch zone discrimination technique. But the system does have the capability to use these, and they also have a very important purpose in many cases. They can really give us some more data information. So here we see views if you've used an OmniScan or Focus LT, more accustomed to what you might be used to looking at. So we have like a C-scan as well as an S-scan with a weld overlay of the joint, and again a linear scan with the weld overlay as well. So often these are used for extra information or added information to be able to discern geometric reflectors or do some tip diffraction sizing. So the zones are very good, but having this added benefit in some cases, the ability to add sector scans and electronic scans selectively, could be very good for certain joint designs. We get the weld overlay display if we have things like high-low, root reflectors, cap reflectors. Going to these channels can give us extra information to be able to make the right analysis. So we'll look at that in a little bit more detail in the next few slides. So if we look at the root, we can use sector scans or linear scans that focus only down at the root. And this will give us a separate view and display. So in this case, we have a lot of geometry that's coming off the root based on its angle of incidence to the sound. And we're able to clearly see different reflectors in both the C-scan and the S-scan that's going to help us make the right interpretation or sizing. So it's a very valuable added add-on to the single beam zone discrimination technique. Different reflectors there that stand out from the geometry. Same thing with the cap, another place we often use the complementary sector scans. Up here at the top, there might be some geometry signals that come from the top or unique defects that happen at the top. We're able to use a sector scan, separate channels with the overlays to help us make those distinctions. The unit itself is a basic Focus LT from the architecture perspective. So the full ability to use this unit really gives it the ability to be used in all types of inspections. So it's usually bought for the ability to do the zone discrimination pipeline, but it could be used for other applications where you just need sector scans as well. You really have full capability of the software itself to apply to any phased array inspection. So quick calibration and adjustments. Again, just like everything else, the calibration has to be quick. Typically after we did the setup, we have our cal block. We'd run a basic scan, and it's going to come up with an output. So this looks very busy, but we have different reflectors. If you can kind of visualize the Z block that I put up earlier. We have all of our zones, and each target is coming up with a certain amplitude. We have some volumetric channels and our coupling channels here. So in order to make these adjustments, we have many, many reflectors. It has to be very quick. So the software here, again, is very smart. We're able to select individual zones and position cursors, and we have automatic readouts. I'll get some little display here. So we have some quick adjustments. If I pick a certain zone or a group of zones by highlighting many of them, what it does is it's going to have each channel or zone, and it's going to tell me immediately what the amplitude is, as well as how much gain it would take to get to my calibration level, which might be 80%, and also for the gate. So we're basically concerned with two things, the amplitude of the reflector and the position in the gate. We want the reflector to come up right in the middle of our gates that we set to be accurate. So here we have a quick adjustment where it's going to show me those readings, and I can either select one channel or all of the channels and say adjust all. It's automatically going to apply the right amount of gain and the right amount of travel delay in order to position those very accurately. So we don't have to go through each channel and do a lot of micro adjustments. The software is going to help us to very quickly set up and make adjustments. So here's just another example. So here we have velocity. We can do different calibrations very quickly. So here's basically the two pieces of information if we break it down to an S-scan, or I'm sorry, an A-scan for each zone that we're looking at. In order to position the calibration reflector correctly, we have a gate. We want that reflector to be directly in the middle of the gate so our zone is correctly positioned on the bevel, and just before it and just after it. Also, we have an amplitude. In this case, we're set at 80%. So each time I made one of those adjustments or had the software do it, basically just by saying adjust all, it's making the adjustment in the gate, in the delay, and it's making an addition of gain for each channel to our set threshold for our reject criteria. So it's very quick, very fast. We're basically looking at those two things in each zone when we're doing the setup. And then basically, in order to look at this data very quickly and have the system be fast, we color code everything. So if I'm looking at 15 to 30 different zones, I want to quickly be able to look at each zone and know whether it reaches a reject area. So there's just one example. This can be user adjusted. 20 to 40, we're going to be green. This is amplitude. 40 to 70, red. 70 to 90, which might be our reject level, is going to be yellow. So immediately by looking at all the zones, I can look for yellow and know that I have an A-scan that's reached my rejection criteria or my review criteria. And same with the coupling channels. I want to quickly be able to look at all the coupling channels, make sure everything was good. So in this case, between 40 and 99, below 40 it's going to turn red for me and show me that at that point maybe I lost some coupling. Maybe the inspection wasn't as good as it could have been. Just a bigger trace of that. So it often looks compressed on the zone because we're looking at many zones close to each other. The A-scan can be hard to determine the height, so we use the colors instead. So here's the typical A-scan trace. We can see at the lower end of that A-scan, even though it doesn't look like it's 40%, we know up to this point everything is below 40. Then we reach 40 to 70 in the red, and here we're 70 to 90, and then as it drops back off, we're again. So we quickly can look at the colors and make our distinction of what needs to be reviewed. Just another example of how we use the quick information in the zones. So if we have a colored bar of high amplitude, like in this case, we're basically getting that information that that indication is on the far side of the zone. So here, this is our gate centered on the bevel. By having a high bar, I can quickly look at a zone and know that it's on the far side of that zone. If I have an A-scan that comes up in the zone, I have a very small amplitude bar. Again, the color is there to know its true amplitude, but the bar is short. I know that happened in the first half of the gate. So I can position that either in the weld or on the opposite side. So we use quick analysis tools like that to quickly make the distinction and keep the inspection very quickly. We also have specialized tools, things like wall thickness variation. So often, especially in seamless pipe, it might vary up to about 10% thickness. So we only have one cow block designed on the nominal. We might actually have a few different thickness values. So we actually have some tools where we can design in 3 different inspections happening at once using only one nominal cow block. So we actually create 3 beams for each zone. In this case, it was 18, 18.7, up to 19.33. And that way, when we scan, we'll do a quick thickness measurement and know which criteria to apply and only have to do one inspection, even with wall thickness variations. So kind of a very useful tool, especially for seamless pipe. Interpret analysis, going to go pretty quickly through this. Once we get our data out, we're able to position cursors. Quick tools here will tell us the amplitude between those, the position in the gate. And then actually we can select multiple channels and be able to get a cumulative type values for length. And then depending on if we chose 1 or 2, it's going to show us the position both in the height axis with all of our values, as well as the position around the circumference of the pipe. Be able to label the defect accordingly, whether I reject it or accept it, and enter it to a report very quickly. There is a close-up example. In this case, we have one zone selected, one defect, called the lack of fusion. I have the start and stop or length, the depth, and the height. I can add some comments, do different things about merging defects, more complex, or just add it to the report. Sample the report, we can get all the bevel design, the cow block design, everything imported directly, and an illustration and additional information about each defect. So some of the key points about the PipeWizard itself, the technique, highly reliable, compact, modular. Very user-friendly advanced software, again, for the zone discrimination technique to keep up with the pipeline creation process. Every single step needs to be very rapid. So we have fast setups, very rapid and accurate analysis, and rapid training based on the user-friendly software. Ability to use sectorial linear scans, along with the strip charts and time of flight diffraction, really allows it to be a full-use phased array system, not just usable in a pipeline zone discrimination situation. Very high accuracy and defect height sizing, which often allows us less rejects. A great alternative to radiography technique, typically about a 0.5 millimeter to 1 millimeter sizing in the height axis. Advanced capabilities, so we can do special configurations like special pipe materials, very thick wall, and also very thick pipe, also with wall thickness variations, and all the TomoView 2.8 software features are available to use it in a lot of different capacities. Very short AUT inspection cycle time would keep up with the high production rates of pipeline construction. Been qualified for all major pipeline projects in the world and pre-qualified by many companies. Suitable for both onshore and offshore, code compliant to pipeline inspection codes, and also durable and rugged for all the different conditions it might meet. Just a little bit about the support. So one thing Olympus has tried to do is put a global support team of our various offices around the world, so we're able to offer fast spare parts no matter where the project is. So everywhere from India to Mexico, we either have a direct office or a distributor or representative, and often we house the correct amount of spare parts. And if there's a project with a client that we know is going to be, we can try to set things up ahead of time so there's not a large delay in receiving spare parts or support. So that's a quick run through about the basic information. I'm going to go ahead and share my desktop because I realize some of the things are hard to see. So this is actually part of the PipeWizard software. This is when we talked about setup creation. So I've already pulled up a setup. We've already went through the process of defining our colors, our thresholds. We've already defined our bevel very accurately based on a drawing from the manufacturer. I must have changed something. See if I can fix that. Sorry for that. Oops. Give me 1 second. See what changes that makes. Just re-pull that up here in a second. Sorry about that. All right, so here we go. So here we just are able to choose each one of our zones, and I can look at how the beams were calculated, where it's going, the angle, the type of elements that are used, which pass it is. And I can also go and look at, when it's all done, all the beams. So this is the basic process. After doing the joint, I basically just hit adjust, and it's going to throw all the beams in there and give me a theoretical positioning. I'm able to go back to the cal block, make micro adjustments by going over each reflector if I want to get a very good starting setup. So once that's done, I can go back and do some micro adjustment. If we look at the after effects, so here's a pretty typical display of the data. So here we have cap, different fill zones, each individual zones. We have some volumetric channels set up in a B-scan type imaging. We have a TOFT channel for volumetric coverage, which is also displayed here. And then basically the same thing for the downstream. So all this would be one side of the weld. This would be the opposite side of the weld. And then we have some couplet channels here that are going to measure. We have different displays, so often an operator will set up 2 or 3 up to 4 main layouts so he can manipulate this data very quickly and look at various things and do the analysis in a rapid rate. So you can see here, if I highlight a different channel, we're able to look at many pieces of information very quickly. If I just position my cursors, we're basically looking between those cursors. So if I make it very wide, I'm actually looking at everything in between. It's going to go to the biggest. But if I hone it in on a certain reflector, right now I'm looking at just this one channel I highlighted and only the things between my cursors. We're able to get quick information. So this reflector has 49% amplitude. It's going to give me the position in the gate, depending on the size of the gate. Giving me the position in the scan axis, so we can kind of see how that lines up with about 50 millimeters. Get that information very quickly. And then by looking at the color, I'm actually able to see the relative amplitude. So these are the type of tools, the color coding, the height of the bar, as well as the quick information here that allows the zone discrimination analysis to happen very quickly. Back to that. So that really brings us to close to the end of our 1 hour here. I will go ahead and see if there's any questions in our thing I can answer in the last few minutes, which it looks like there is a lot, so let me see. Can we use the OmniScan MX2? No, the OmniScan is really based on being a general practice open field unit. It really isn't equipped to do this. You can see throughout the presentation, the real core of this system is the PipeWizard software itself, along with the strip charts and the things. It's really a complete system that we try to use. Using OmniScan MX2 is not really equipped to do this. Code requirements to use transverse. Yeah, I don't know off the top of my head. I wasn't really ready for sections and things. It's really down to the pipe. Depending on the welding process, the customer requirement, there'll be certain piping that might experience transverse type defects, and this would be the case where we'd consider using the transverse module. To the code level, I'm not sure if there's a particular area within the STM document off the top of my head that specifies the use of transverse detection. But it's something we can follow up on and see, but I think it's more of an application and customer requirement. What is, another question here. Good question. I'm talking about the accuracy of probe scanner positioning. We talked about how in order to pull off the zonal discrimination where the beam is hitting very accurately for the multi-zonal technique, the question is, what is that accuracy of probe positioning? And it's typically about 1 millimeter or less. We want to hold that probe to a very tight mechanical position, both from skewing left and right or forward and backwards. So 1 millimeter is typically a good number to use. 1 millimeter or better is what we try to hold with the PipeWizard mechanic. How does the technique accommodate pipe thickness variation? I think this was probably asked before going over that slide. So basically there is some adaptation, especially for seamless pipe. We allow multiple setups that fit a range, and then we take a measurement and we apply the most suitable setup that are all acquired at once and use that criteria or that setup information to do the analysis. See if there's another good question, a lot of the repeat ones, so we'll try to find another few good ones before our time ends here. Question about slides. What we're going to do is we're going to actually post this to our website. We'll have a live version of this recording along with the narration and probably a question and answer. So best place to get any of the information is directly after we post it to the website. A few more questions. See, I'm just going through some of these. How to find length. I think that might have been asked. Maybe it was covered. Maybe it was unclear. Various different ways we can position the cursors around a zone or multiple zones, and it'll actually give us cumulative length based on different thresholds that we set. That can also be verified if we have separate sectorial, linear, or in the volumetric channels. Really find length in a variety of different ways. The quickest way is by looking at zones and using the cursors and setting some criteria for the length sizing. Lots of the same questions. Question, the zonal technique good for single V type joint configurations? It's not the typical use, but it can be used on this type of joint. Whether or not there would be a need for it for a single V, it's definitely something to be investigated based on what it is. The system's fully able to be designed with a single V type joint into the software and calculate the beams. Really, to ensure the inspection's good, you would just have to have a good calibration block built with the correct reflectors. Going through a few more. I think we have time for a few more questions maybe. Question for different diameters or small diameters, do we use any curvature type probe or normal one? Yes, so depending on the outside diameter, just like the normal use of ultrasound or normal phased array, will adjust the curvature of the wedge so that we get a correct fit on the pipe, proper coupling. Typically, depending on the diameter, a single range of curvature will actually fit a range of diameters with the usually accepted required gap minimum, usually about 0.5 millimeter or so in most codes, and you're able to use a wedge across a range, but in order to do a wide range of diameters, you will need a certain series of curved wedges. Question more about the thickness variation again. Is it possible to do assessment after scanning? Yes, so generally the technique is to scan with 3 different beams or 3 different setups, if you will, and then afterwards, based on the actual thickness of that joint, you will choose which beams to use or which analysis data to use, and you can do this after the scanning is done. Another question, maybe we covered it after the question, but is it possible to judge the length just how we are judging the amplitude? Yeah, so typically what we do is use the cursors to get the quick length, either in one zone or cumulatively. So we do have a quick analysis feature where it's going to show us in the top what that length is, and we can use other parts of the software to verify it, to judge it. But we do have a quick way to easily judge the length of the defect very quickly, as well as cumulative zones, cumulative defects together. We can judge the entire length based on some criteria that we've set for the inspection. So there's lots more questions. We're not going to have time to get through all of them. We will go through all of them and try to answer them all, either directly on the website or in private emails. So if we didn't get to your question during the webinar, we will answer them at a later time. Thank you again for joining, and at this time I'll turn it back over to Greg.
Thanks, Nick. On behalf of Olympus, I'd like to thank all the attendees for joining us and Nick for his expertise in today's event. We hope this material was informative and useful. This information, along with the Q&A session, will be archived on our website at www.olympus-ims.com. Everyone who registered for this event, whether you attended or not, will receive a follow-up email with links to the archived webinar. That's going to do it for this morning. Thank you for attending, and we'll see you again next time.